Good afternoon, everyone. Can you hear me? Oh, great. Okay, so exam 2 went much better than exam 1. The average grade was about 13 points higher on exam 2. And if it wasn't for question 3, which 92% of the class missed, then the difference probably would have been, 21% difference. So that's good. I think it's at least partially due to the having less questions, having 12 questions instead of 15. But if any of you have any feedback on that, I'd be very happy to hear it. Feel free to send me an email. So this is a distribution. It looks like 80 to 85%, or it's 21 students out of about 51. We're in the range of 80 to 85, and I think so each of these questions is worth 8.3%. So each one of these bars, every one of these histogram bins represents one score essentially. So that's why I guess it's not possible to get between 85 and 90 if you're in increments of 8.3, I guess. So that's why there's no one in that category. Likewise for 70 to 75. So about half the class got 80 to 85%. So there will still be, obviously, looks like there's going to be a curve at the end of the semester. I don't know what that's going to be yet. We are not planning to drop any grades, which is something that we have done in previous semesters. But because everything for this semester is new, we didn't plan for that. And I realize it's a little unfair to you guys not being able to tell you what the curve is going to be, because that makes it so you don't really know where you're standing. But I'm not sure how to solve that problem. But I think that the quizzes are generally very good, and I'm not sure about the projects yet because we've only had, I think, the project 1 graded so far. So there's a chance that the final scores will still be pretty good, even though the exam scores are lower. But I'm not sure. I'll try to give you more information about the grade the kind of the total overall grade distribution as soon as I have a better picture. Charles is going to work some magic here. I asked him to take a look at what the distribution, or at least the distribution and the average exam scores were among the 12 or so students that are actually in the lecture.
I'm still typing because there's no
Okay.
no convenient way to extract this from Blackboard while it's running.
Okay, yeah, so that's okay. Just chime in whenever you have it, Charles. I'm just curious because I suspect that if the average for the class is 77.1, I'm going to guess that the average among the 12 students that are in the lecture here I'm guessing it's going to be 85, maybe higher. Just a guess, though. See how close I am. So yeah, it pays to attend lectures, I think. Yeah, so this is the distribution of exam 2 versus 1. You can see the exam 1 had a very high variance, so you can see that standard deviation. So the scores are spread out more, whereas exam 2, everyone's kind of seems like half the class is in that 80 to 85 range. Okay, so I'll quickly go over the exam questions just because the final exam is comprehensive, and I want to have this review on record. Make sure I'm recording here, right? Yeah, I just want to make sure that I'm on record as going over this, so when you're studying for the final exam, you can go back and review these review lectures to refresh your memory about these old topics. Oh, sorry. Yeah. Okay. So, but I'll go through this quick. If you have any questions, feel free to chime in and ask. So assume you measure a task's execution time for 6 runs as 12 milliseconds, 14 milliseconds, 11 milliseconds, 25 milliseconds, 31 milliseconds, 32 milliseconds. What's the worst case execution time at 99.9% confidence, assuming the first and second 3 measurements are generated from 2 separate control paths? So you calculate the mean and the standard deviation of the first 3 and the second 3. So the means are 12.3 and 29.3, and the standard deviations are 1.5 and 3.8. And so the high limit is the mean plus 3.09 times the standard deviation at the 99.9% confidence interval. And so the highest of the two is going to be the second group, the 29.3 plus 3.09 times 3.8. So the mean, and then you add 3.09 standard deviations to the mean, and you get 41 milliseconds. Assume 4 tasks with execution time period values of 315, 720, 525, and 730. What is the utilization? You just add up the ratios of execution time to periods, and you get 98.3%. Assume 3 tasks with execution time period values of 210, 720, and 1840. Are they schedulable with RMS on one processor? So if you add all those up, it equals 1. That's 100% utilization. This was the question that 92% of the class got wrong. I think the reason why is because if you do the RMS schedulability test on these, it'll be negative. Right? You'll end up with a calculated value that's greater than 2. But remember that only means that you can't guarantee schedulability. It doesn't mean that you can't schedule. And if you add up the utilizations, you get 100%, which means that you can schedule this with EDF. But the reason why you can also schedule it with RMS is because the periods are mutually harmonic. And this was, obviously I didn't emphasize it as much as I should have in the lecture, but it's, I think it's on slide 25 where I mentioned that. Oh, okay. Well, that's okay. Okay, Charles, do you want to say that? That's okay.
Yeah, sure. I can screen share the figure too. Yeah. So we got it actually turned out, I'm surprised the mean among lecture attendees was actually just a bit lower. Among those present today, it was 7.3 out of 10 compared to an 8.05 out of 10 through everyone not present today. And hang on, once I finish, figure out how to screen share, we will see a pretty histogram.
I might have to stop sharing. I stopped sharing. There we go.
So yeah, it's this is the there's bin sizes are 1 out of 10, and so all the stuff in blue, all the stuff in blue is people that are present right now, and the orange is absent, and then the number of occurrences is y-axis, and right. So if you were in the rightmost column, you got an A, and if you're in the leftmost column, you got a 0. Fortunately, I don't think anybody was in the leftmost column. What I would have really wanted to do would be do a scatter plot and have on one axis be number of lecture sessions attended, and on the other axis be score on the midterm. But unfortunately, there just isn't a good way to handle that through Blackboard, because you can't see when people attended previously, which is surprising. But yeah, so surprising result.
Yeah, I wouldn't have guessed that. So I mean, so that means statistically, you did worse on the exam if you're here right now. So yeah, none of you guys should be watching this live.
I did try looking at the attendance reports. I don't think we had those turned on, and I don't think it can do them retroactively. I think I turned them on today, so I guess we'll see if it works then. Attendance is not a grade for this class though, so even if Blackboard tells you something about, oh, you've been marked whatever for attendance, just ignore it. We're not doing it just for information purposes. But I don't know, my hypothesis is maybe the people that did really well on the exam were like, yeah, okay, I'm doing pretty good. I don't need to pay attention to lecture. I don't know.
Yeah, it could be. The reason I asked was because when I taught 611 last semester, I did the lectures asynchronously. So I would just post them and then just give everyone, everyone would watch them whenever they wanted to. And we got a lot of negative feedback from that. So I assume that the live synchronous lectures would have a positive impact, but evidently they don't. Okay, yeah, sure. Let's see. Question. Wait, hold on one second.
I'll go ahead and stop sharing. If somebody really wants this figure, I guess let me know. And I'll also just paste these stats in the chat in case anybody is really super interested in the stats.
Okay. Okay, so sorry, we had a question about everyone. Problem 1. Okay, sure. Standard deviation for problem 1. Okay, let's check it out. I'm going to share my whole screen. Oh, okay. Well, that might be a mistake then. And if it is, we'll fix it. Let's see, share. I'm going to share the whole screen so I can pop MATLAB up. So when I did the standard deviation, I used MATLAB. Okay, yeah. So let's go ahead and let's do it. Okay, so standard deviation of 25, 31, and 32. So let's copy this and paste it there. Okay, so MATLAB is still telling me 3.7859. You guys see that? Sorry, I don't know if you can see that. Hopefully you can see that. I'm sharing my whole screen here. This is how I did it. Maybe I'm missing something. Charles, can you confirm? Can you use NumPy and check standard deviation at 25, 31, and 32, or Wolfram Alpha? That's another option too.
Sure, hang on, sit tight. I got to remember how to actually do that.
Could try Wolfram 25, 31, 32. Wolfram Alpha. Standard deviation of 25. What is it again? Oh, wait a minute. Is there a comma or no? That's right. Yeah, 25, 31, 32. 25.
So I am getting a. Oh, does this not tell me the standard deviation? It only tells me the variance. Rip.
So Wolfram is also saying, Wolfram agrees with MATLAB that it's 3.7859. That's exactly what MATLAB said with 5 significant figures.
I got 3.785 with Python's standard deviation implementation.
Well, I'm sorry, what was that, Charles?
I got the standard deviation of 25, 31, 32. I got 3.785.
Okay, yeah, that's similar. 70, yeah, it's actually, well, MATLAB would have said, if it rounded, it would have said 3.7.
I didn't read all the significant digits. I actually got 3.759388972001824.
Okay. So I think what happened is you guys didn't divide by, or didn't multiply by 1 over n minus 1, which means that you divide by 2, right? Maybe you divided by 3 when you found the differences with each value in the mean. Yeah, I think that might have been what happened. Okay, yeah, okay. Well, that explains it. Yeah, so I think that should be right. I mean, it's been I took statistics in 1996, so you guys have seen it more recently than I have. If I'm wrong, let me know. Okay. Okay. So yeah, if you guys have any if there's an issue with that, let me know. Okay. So let's see, where are we at? Right. So okay. So I'm gonna go ahead and do full screen. Okay. Assume three tasks. Yeah. Assume three tasks, 1, 2, 3, with execution on period values of 1, 5, 5, 7, and 511. Are they schedulable using partitioned RMS scheduling on two processors? If so, which task processor assignment is schedulable? The key word here is partitioned RMS scheduling. So you have to basically look at every way to assign those tasks to each processor. If you assign all three to one processor, the RMS bound value is 2.99. If you put 1 and 2 on one processor, tasks 1 and 2 on one processor, let me say, if you assign tasks 1 and 2 to processor 1, the RMS bound is 2.06. If you assign tasks 1 and 3 to processor 1, you get an RMS bound of 1.75, and then of course that only leaves task 2 on the other processor, and the utilization there is only 71%, so that one is fine. And then if you assign tasks 2 and 3 to processor 1, you get an RMS bound value of 2.49, or actually not bound value, but the RMS schedulability test value, I should say, rather. So if the RMS schedulability test value is greater than 2, then you can possibly schedule them. But if it's less than 2, then you can schedule them. So we know that we have at least one assignment here where it's schedulable. So the answer is yes. Assume 4 tasks, 1, 2, 3, 4, with runtime period values of 6, 8, 10, 12, 12, 16, and 10, 20. Are they schedulable with EDF on 3 processors? So you calculate the total utilization is 280%, 2.8, which is less than the max, which would be 300% if you've got 3 processors. And the greatest common divisor of the periods is 4. And so you multiply 4 by each of the ratios of runtime to period, and one of those gives you a fractional value, which fails the schedulability test. However, if you were to change the execution time of that task, which would be task 2, if you change the execution time from 10 to 9, then you would get a an integer value, integral value there. So I think one of the answers was it's not schedulable, or maybe not schedulable, but if you assign if task 2 were to have a slightly lower execution time from 10 to 9, then it would be schedulable. Okay, this next question is assume 3 tasks, 1, 2, 3, with worst case execution time and deadlines of 310, 420, 610. What is the scheduling order under non-preemptive least slack first scheduling? So this one, I didn't talk too much about this, but it's an easy question. The slack is the difference between the deadline and the execution time. And so in that case, if you calculate the slack for all 3 tasks, the one with the minimum slack is 3, and then the next lowest slack would be 1, and then finally 2. Next question is assume a queuing system has an average arrival rate of 1.5 customers per second and contains 25 customers on average. What is its waiting time for the whole queuing system? This is just an application of Little's law, which is L equals lambda times W. And so L is 25. It's the number of customers in the system on average. The average arrival rate is 1.5 customers per second. And we're calculating W, so W is just 25 divided by 1.5, which is 16.67 seconds. Let X be an exponentially distributed random variable with rate 0.5 events per second. What is the probability that X is greater than 4? For this, you would use the complementary cumulative distribution function, which is just e to the negative lambda t. So lambda is 0.5, t is 4, so it's just e to the raised to the negative second power, which is 13.5%. Does that pass the sanity check? 0.5 events per second. So an event every 2 seconds. What's the probability that 4 seconds will elapse between events? Yeah, seems about right. 13.5. Yeah. Assume the Carolina Gamecocks score touchdowns according to a Poisson process with rate 0.3 touchdowns per quarter. What is the probability that they will score 2 touchdowns by the fourth quarter? So this is the Poisson process equation, which is P sub 2. I always, this one, I don't know why, I always have trouble with the variables, but with this. But P sub 2 is the number, N, 4 is the time, so P sub 2, 4. So the equation is lambda t raised to the nth power over n factorial times e to the negative lambda t. So you're going to put 2 in for n and 0.3 in for lambda. So there's your 2 in the denominator, 2 factorial. There's 2 is in the exponent up here. Lambda is 0.3, and then over in the exponent for e, you've got 0.3 and 4. And so you evaluate that out, and it comes out to 21.7%. So yeah, they're scoring about 3 touchdowns a game, or sorry, 1.2 touchdowns a game or so. So there's a 21.7% chance you'll have 2 touchdowns by the fourth quarter. Right. What is and by the way, this is because the time unit here is quarters. So the lambda is given in touchdowns per quarter. So T is in terms of touchdowns, or in terms of quarters rather. Okay, what is the expected number of customers waiting in the queue in steady state for an MM1 queue with lambda 7 per second and mu equals 12 per second? The reason I spelled out lambda and mu here is because I don't know. I'm sure there's a way to put these symbols into.
I use GNOME characters to it lets you search through, like, fuzzy find all the Unicode symbols, and then you can just click one and it'll copy it to your clipboard.
Okay, what is it called? GNU characters?
GNOME characters. I'll send a link in the chat.
Oh, okay. Okay, cool. Yeah. I think, I mean, there's a Windows character map, but it's not. There's no way to look up characters in it. You have to kind of scroll through. So, but yeah. So sorry about that. So this is the equation. Now, if you miss this question, you might have used the wrong L equation. Remember, there's 2 L equations. There's 2 equations. One of them is the average number of customers in the queue, and the other one is the average number of customers in the whole system. Oh, that was Charles, right? Was that you, Charles?
Hi, that was.
Yeah, thank you. Yeah, so the queuing system includes the queue and the servers. So you have to differentiate. When you have L, you have to differentiate whether you're talking about, number of customers in the queue versus the number of customers that are in the whole system. So L sub Q is lambda squared over mu times mu minus lambda. So the equation is, itself is simple. You're just plugging in values, but the trick here is to make sure you use the right equation. So it turns out it's 0.82. What is the expected steady state waiting time in the queuing system for an MM1 queue with lambda equals 7 per second and mu equals 12 per second? So the lambda and mu are the same as they were in the previous question, but now I'm asking what is the expected waiting time. So you have to calculate L. Now this is not L sub Q, this is just L now. Even though lambda and mu are the same, we're calculating a different L. This L is lambda over mu minus lambda, which is 1.4. So there's on average 1.4 customers in the system, but only 0.82 customers in the queue.
May I ask a question?
Sure.
So I noticed that the difference between this one and the one you had on the quiz was the parenthetical that mentions the queuing system. So when you say that, you don't mean the system that operates the queue, you mean the queue and the system, right?
Yeah, the terminology is a little weird. So the queuing system includes the queue and the servers. The servers are whatever entity is processing the customers. so I try to be consistent with the terminology. I call the servers, and then the system is the whole system. So yeah, that was what I meant by queuing system. You might have, when you saw that, you might have thought I was talking about the servers.
Yeah, I used L sub Q. Yeah, L sub Q.
L sub Q would be, I guess. Let's see, if you knew L and you knew L sub Q, I guess the difference would be the average number in the servers, right? Like, so if you had L and you subtracted L sub Q, then you would be saying the number of customers in the system minus the number of customers in the queue. That would give you the average number of customers in the servers. Which now that number couldn't exceed 1 in an MM1 queue because there's only one server. But it could be less than 1 because you could have idle time in the servers. So if you on average had 0.5 customers in the server, that would mean your server is idle 50% of the time. That would have been a good question to ask. I didn't just thought of that now. But yeah, that's the terminology. Yeah, that's the I probably should have emphasized that more. But yeah, the servers are, and you can have more than one server. We just didn't do that in this class.
So, sorry, my computer blacked out. Did you say anything? I heard yeah, you mentioned the two values.
Yeah. So there's L sub Q is the average number of customers that are waiting in line, and then L is the average number of customers that are the combined total of average number of customers in line and being served.
Yeah.
And then I was saying that if you take the difference of those two values, you would get the average number of customers being served, which might also be a useful value as well if you're concerned about like idle time on the server. Like if you want to know how long the server stands around not doing anything, then that would just be the difference of those two.
I see. I guess I was confused because it didn't have that terminology in the quiz, but I know now.
Okay, yeah, sorry about that. I have to go back and look. I don't remember how I worded it in the quiz. I wasn't looking at the quiz when I wrote this. Okay, so for this, once you have L, then you just use Little's law to get W, which would be 1.4 over 7, right? Yeah, which is 0.2 seconds. So that's pretty short. What percentage of time will the queue be empty? For an MM1 queue with lambda equals 7 per second and mu equals 12 per second. Again, it's the same lambda and mu, but we're calculating the percent time the queue is empty. I think this was this is the question that had the lowest average score on the quiz. And so that's why I put it on the exam. So this would be the probability that there's no customers in the system plus the probability that there's one customer in the system would represent the percent of time the queue is empty. Because if there's one customer in the system, they wouldn't be in the queue, they would be getting served. So that would be 1 minus rho plus 1 minus rho times rho, which turns out is 66%. Okay, and that's it. That's queuing theory and real-time scheduling. Any other questions? Okay. All right, I'm gonna switch now to, I just want to share PowerPoint. Okay, so now we're going to, the course is going to kind of shift quite a bit. So we were talking about kind of theoretical stuff, conceptual stuff, mathematical stuff. Now we're going to make a hard turn into hardware and low-level stuff. Some of this material I cover in my 611 class. Right at the end of the semester, I get into CMOS logic and transistor level logic, and even I talk even a little bit about noise and signal integrity. But generally, that comes right at the end of 611. And I think that's a better topic for this class. This class is about systems engineering, and we want to be able to understand, why is SPI so slow? Why is an Arduino slower than a Xeon? Why is that? Why does clock rate get faster? Why is the clock rate so slow on some processors and so fast on others? Why can't we, run these interconnects faster and so forth? Or, for example, why does distance matter in terms of, error rate and transmission speed? Well, generally speaking, the answer to all those kind of boils down to CMOS technology and semiconductor technology. And so I want to talk about that. I think this is a good place to cover it. And these are all considerations for processor technology and interconnect technology, how fast you can control things and how fast you can run a processor and that kind of stuff. So this is we're basically talking about devices. Now you might say, oh no, this is an electrical engineering topic. This is stuff that we cover in 371. No, actually 371, for those of you that are taking that or that will take that, that's more of that's an electronics class, but it's more of an analog electronics class. And we've actually eliminated that class from the computer engineering curriculum. If you are still on the curriculum that requires that class, you have the option to switch to the newer curriculum and not have to take it, in which case we've replaced it with Electrical 201, which is the lab that goes along with the Circuits 2 class, Signal and Systems, which is arguably also an analog class, but it's a little bit, less so. And we thought that would be more applicable. But anyway, what I'm talking about here is digital. I'm talking about digital electronics. How does digital electronics work? Oh, sorry. 201's not being offered? I would expect that to be every semester, since it's all the electrical engineering students have to take it, I think. I have to look at that. I wasn't. Yeah, 491. This is 491. You guys are in 491. This class is going to transition to become 491. So don't worry, you're already taking 491. It's just a different name. Okay, so let's see. Yeah. Okay. So how does semiconductors work? So chips are made of silicon. I'm sure you know that. Why though? Silicon is a semiconductor, which means that it. Well, let me clarify here a minute. So silicon can exist in two forms. It can be in a glass form or it can be in a crystal form. When you talk about silicon semiconductors, you're generally talking about a crystal form. So if you have a crystal of silicon, which is where you have a silicon that's in a lattice and it has covalent bonds with 4 of its neighbors, it's a crystal. It's in the crystal form. Crystals are grown, as you probably know. And silicon crystals are grown into an ingot and then sliced into wafers. An ingot is just a cylinder, big cylinder of silicon. So semiconductors are very, very bad conductors. They're not considered insulators, but they're horrible conductors. But the nice thing about silicon is that you can change its conductance property by doping it, which is where you basically inside of a fabrication plant, you take the silicon wafer, which is a disk of silicon, and you use gas deposition, where you basically heat it up and you expose it to a gas that contains another element. And if you heat it up enough, that element will inject itself. It will invade the silicon crystal lattice, and atoms in that element will replace some of the silicon atoms in the lattice. This is called doping. And so if you take an element from column 3 in the periodic table, so silicon is in column 4, it has 4 valence electrons. If you take an element from column 3 that has 3 valence electrons and you dope it, you send it into the lattice, you have it invade the silicon lattice, then certain silicon atoms will be replaced by, for example, a boron atom or a gallium atom, and that will basically have if you do it with a type 3 or column 3 element, you get holes, you get a lack of an electron. So you still have the crystal structure, but you have an element in there that has one less electron than it's supposed to have. And that lack of an electron is actually mobile. So meaning that, now you might say, how could a lack of something be mobile? Well, it's because, like, for example, if you have a boron atom over here in the lattice, then it only has 3 electrons, but it can borrow an electron from its neighboring silicon atom, in which case the lack of an electron would then move over to another one of its 4 neighbors, basically. So that lack of an electron can move around, and that becomes a charge carrier. And that increases the conductivity of the lattice, right? Now you might say, what's a charge carrier in general? Well, if you've ever seen, like, if you have like 2 electrodes and they have a very high voltage potential, and you move them kind of close together, eventually there'll be an arc of electricity that'll go across. And that is because the air in between the 2 electrons becomes ionized. And ionized air is a charge carrier, the ions in the air. So air is an insulator, but ionized air is a conductor because it has charge carriers. And it's the same idea. You have these charge carriers that carry current through the semiconductor. And so if you can do more doping or less. The level of doping you do defines how many of those silicon atoms get replaced by the dopant atom. And so you can dope very heavily, in which case you have very good conductivity, or you can dope a little bit, in which case you don't have as good conductivity. Likewise, you can dope with an element from group 5, like arsenic, for instance, in which case you get an extra electron in there that can move around the lattice, and it becomes a charge carrier, so that will conduct, allow it to carry current. Charge carriers is a way to convey current. It's a way to conduct electricity. It's charge carriers. So you have a choice. You can use a group 3 element, and you can dope your silicon. That will make it a p-type silicon because it's a positive. P stands for positive because there's these holes. Or you can use a group 5 element, in which case you get an n-type silicon, which stands for negative. N is negative, and because electrons are negative, and electrons are the charge carriers. And so that's how you change the conductance. Now, the thing about that is, and this is the part that I always found a little confusing, is that the charge carriers, obviously you get holes for p-type, and you get electrons for n-type, as I just explained, but those are the majority charge carriers. It turns out that when you do the doping, you also get the opposite type of charge carrier in there as well, but it's not as predominant. It's called the minority charge carrier. So you have majority charge. So in an n-type silicon, the majority charge carriers are electrons, and the minority charge carriers are holes. Whereas in the p-type silicon, the majority charge carriers are the holes, and the minority charge carriers are the electrons. Right? It's opposite. Assuming I didn't screw that up. Right? So anyway, this is the lattice. I think this is kind of neat. This shows the lattice is a 3-dimensional structure where every atom connects to 4 of its neighbors, and this is the unit cell. The unit cell is so all of those, the lattice, each of these atoms is connected to its neighbors through a specific angle, which creates this structure. And this structure, which has, I think, 16 atoms in it, is repeated, right? So they call it the unit cell. Now, the distance between these atoms is about 0.5 nanometer, right? Which is in the whole cell, which is the repeating unit, is about 5 nanometers. Now, you might say, well, why is that significant? Well, you may know this, but modern semiconductor technology allows you to make transistors that are 11 nanometers, right? What is the current? What, 12? 11? So basically, that Moore's law is going to end because the size of these transistors is actually approaching the spacing. Well, it's already kind of hit the cell size, and very soon it will eventually, it'll get closer to the spacing in between the individual atoms, the atomic widths. So that's kind of crazy. Matthew said, why does the structure of silicon need to be a crystal? if it's not a crystal, it has to be a crystal for it to be a semiconductor. The other option for silicon is to turn it into a glass, and generally that's when you oxidize silicon and it becomes silicon dioxide, and that's a glass. And glass is actually a very good insulator. It's a total insulator. You can't dope silicon dioxide because it's not a crystal. So because you can't dope it, electricity doesn't pass through glass at all. And in fact, they use glass to separate the layers on a chip. Glass is a really good insulator in the sense it has a good dielectric constant. Gas doping is the same as, I'm not sure if so semiconductor technology, so the reason why Moore's law exists, by the way, is because the process by which you make these chips is improved. So, you know, originally they use photolithography, which is where you basically, you create a mask that's a photograph and you shine light through it, and that softens the photoresist that creates the different patterns on the wafer. But the problem is that you can't shine light through an opening if the opening is less than the wavelength of the light. And so as they shrunk down these features small enough, at some point they couldn't put light through it anymore. It became opaque because, you know, it's basically, if you have if you have a mask and you put a hole in it that's smaller than the wavelength, the light won't go through. So they had to switch to like an electron beam instead that had a shorter wavelength. And so they've made continuous improvements. And the gas deposition, which is how they dope the silicon, is part of those improvements. And so you could be right. Chemasorption might be the new way they do it now. Maybe the gas deposition is the older way. You know, obviously, as you make the chips, you make the features on the chip smaller, you know, some of the old techniques for doing doping and masking and all that stuff don't work anymore. So they have to switch to these new techniques. So yeah, you could be right. I might be using an old term. I've never been actually in a fab, so and I'm not a fabrication guy. And you might be saying, well, then why are we covering this? Well, because this stuff becomes relevant when it comes to figuring out, you know, how fast you can run a chip. Trust me, this will eventually go somewhere. So, okay, so I talked about P silicon and N silicon. They're semiconductors. Okay, fine, they're conductors. What's, you know, so we can conduct electricity. Who cares? Well, something really crazy happens if you take a P-type and an N-type and you mash them together. It creates a diode. And what happens there is if you put a positive voltage on the P-type side of the diode, that creates a positive charge relative to the voltage on the N-type. And if that happens, the majority charge carriers, which are holes on P-type and electrons in the N-type, they move together to the junction of the two. And they allow electricity to flow. They allow current to flow, sorry, from the P-type to the N-type. The P-type is the anode and the N-type is the cathode. But if you reverse bias, if you put a negative voltage on the P side and a positive voltage on the N side, the negative charge, the negative voltage on the P side will repel the electron charge carriers in the N-type side, and likewise the relative positive charge on the N side will repel the whole charge carriers on the P side. And so it'll move the charge carriers, it just moves the charge carriers away from the junction, and it makes it so electricity, or current rather, will not flow backwards. So you can't send current from the cathode to the anode. That's called reverse bias. Okay, so that's a diode. I'm sure you guys have heard of a diode. Then you can build a transistor, kind of like by putting diodes together, but the way that it operates, it's a lot different. So modern chips are made out of metal oxide silicon transistors, MOSFETs. Transistor. The FET is field effect transistor. So basically, what you have is a structure where you take the wafer. I mentioned there's a wafer, right? So you start out with a pure silicon ingot, you slice it into wafers. Then you dope the wafer. You make the whole wafer be either N-type or P-type. Generally, it's P-type. But you lightly dope it. You don't dope it heavily. It's a very light doping. And that becomes the substrate. So that's kind of the starting point. Everything is kind of built on top of that, right? So then you can build these diffusion areas where you can use masking techniques to mask off a big part of the wafer, the substrate, but you can leave openings that you can then do gas deposition with an N-type atom, and you can switch the P to the N in these little islands. So what I'm showing here is a cross section. This is a cross-sectional view. So it's kind of like looking at, like cutting a sandwich in half and looking at the inside of the sandwich. And so what you've got is the P-type substrate. That's the kind of just a bare disk, the bare wafer. And you can inject these little islands of N-type in there. Now you might say, wait a second, you can't just, I mean, this is electricity. You can't just do that. Well, you can, because keep in mind that if you ground the substrate, if the substrate is kept at ground potential, then there's no way, even though these are two semiconductors that are touching each other, they form a diode, and you guarantee that nothing from that N, that N little well here, that they call it a diffusion area, nothing from that will go into the substrate. It'll be electrically disconnected, even though it's physically connected, because you've got a reverse bias diode. And you might say, well, how do you guarantee it's always reverse biased? You ground the substrate. You keep the substrate at ground, and you can't, it's not automatic. You have to do that. You have to electrically connect the substrate to ground. And if you do that, you won't have any leakage from the substrate into these little guys, right? And so these little diffusion areas become the source and the drain of the transistors. And then there's an area in between that's just substrate, right? And that's that'll become the channel, right, in between. And then over top of that channel, you have a layer of glass, which is silicon dioxide. That's your insulator. And then above that, you have a gate. Now, the gate material so originally they used to use metal for the gate. And then when I was in graduate school, in the 90s, 2000s, they were using polysilicon, which is basically a very highly doped type of silicon. It's what they make solar panels out of. Now they've switched back to metal. We used to teach students that, well, metal, right, that stands for metal oxide semiconductor, which is what you're naming from the top to the bottom here in this stack in between the two diffusion areas. Metal oxide semiconductor. We used to say, oh no, they don't use metal anymore. That was back in the 60s and 70s. Well, they're back. I think they're back to using metal now. So now the term it went from a misnomer to now being accurate. But anyway, the point is that this is a capacitor, basically. You've got a gate, which is a conductor, and then you got an insulating material, and then below that you've got a semiconductor, which is technically a conductor. So you end up with this capacitor. So basically what you've got is these two diffusion areas, and then in between you've got one side of a capacitor, and on the other side of the capacitor you've got a gate. And so that's how it works. You end up with this device that has 4 terminals. It has a source, which is in a drain, which are these two little islands of oppositely doped silicon that are embedded in the substrate. And then you've got a gate that's in between them, which the gate is actually kind of like a sandwich. It's a conductor, insulator, and then the channel, which is the substrate that's in between the source and drain. And that becomes your 3 terminals. And then there's an implicit 4th terminal, which is the substrate, which I mentioned that the substrate has to be grounded. So that's sometimes called the bulk, or the 4th terminal, or the body terminal. And it's usually not, shown in these kind of diagrams, that connection, but rest assured that that substrate is grounded. And it's very important that it's grounded, because if it's not grounded, you'll have this phenomenon called latch up, and your chip will fry. You'll end up with current flowing from the substrate into the transistor terminals here, and it's bad. So you got to keep that substrate grounded to make sure that there's a reverse bias diode formed between the source, gate, and body. Yeah, so that's basically it. Now this will form an nMOS, by the way, and because the source and drain are N material. A pMOS is the opposite type of transistor, and that's when you have P P silicon for the source and drain. I might say, wait a second, you've already got P silicon for the substrate. Well, to make that, wait, do I have a picture of that? Yeah, so to do a P transistor, you need a substrate that's N. And so how do you do an N substrate if you've already got a P substrate? You create what's called a well, which is another deeper diffusion area that encompasses the two terminals. So I won't go into a lot of detail there because you know, that goes a little bit outside the scope. But you can make an N or a P type transistor this way, even if you have a P substrate. And basically the type of transistor depends on what the type of silicon is for the source and drain. And as I mentioned, the substrate is usually very lightly doped, whereas the source and drain are heavier doped. In fact, they usually will put a plus sign. They'll say N plus, but that's not shown in this picture. Okay, so so how's a transistor work? Well, as I mentioned, the P-type silicon has charge carriers in it, which are holes, which are signs, which is why, you know, that's where the P comes from. And, oh, there's the plus sign. Yeah, you see N plus, that means it's highly doped N silicon, whereas the P is lightly doped. But anyway, so you've got this pluses in here. These are the charge carriers. These are the majority charge carriers. And then you ground that, right? And then, for example, then if you put a positive charge, which is also the same as saying a positive voltage on the gate, you get this crazy thing that happens where the gate it's a capacitor. It charges up as a capacitor, right? So you end up accumulating this positive charge on the gate, okay? And then that attracts the minority carriers, the electrons, out of the substrate. Now you might say, wait, like, how do you get minority carriers in there? Well, there's, you know, that's part of the doping process. You've got majority carriers and minority carriers. Even though you doped with a group 5 element, a group 3 element, you still end up with some minority carriers in there, some electrons, and so they will get attracted to the channel because they'll be attracted to that positive charge on the gate. And so what you end up then having is you end up with these electrons that kind of gather inside the channel, and they will kind of physically contact the N-doped silicon of the source and drain, which already has electrons as their majority charge carriers, and you'll get current then that will flow between the drain and the source, okay, through the channel, but only if you've got the gate charged up, right? If the gate's not charged up, then there'll be no current that flows because you'll end up with a reverse biasing, you know, obviously between the source and drain and the substrate. It will be reverse biased, so there won't be any kind of electrical connection. The channel will have majority charge carriers, which are going to be your holes. So basically, this is just a switch, essentially, kind of. Well, it's not just a switch. We'll talk more about how it's different from a switch in a bit. But think of it now as a switch where you charge up the gate, it attracts the minority charge carriers in the channel, and then those minority charge carriers, which are electrons, match up to the majority charge carriers in the source and drain, and it electrically connects the source and drain. Whereas if you don't put a positive voltage on the gate, then it's disconnected. Okay, so this is kind of just what I just got done explaining. So if the gate is 0, which is ground, or anything less than the threshold, then you have this, you see these little diode symbols there. It shows that there's a reverse bias because it's reversed in the sense that you can only send current from the substrate into these guys, but that will never happen because we've grounded the substrate. So by grounding the substrate, we've reverse biased these diodes, and so no current can flow from the source and drain into the substrate or between the source and drain through the channel, right? On the other hand, if you put a VDD on the gate, VDD being the voltage, the supply voltage of the chip, that will put a positive voltage on the gate. It will also charge up the top plate of the gate, which is the top plate of the capacitor. and then that will attract the electrons to the channel, and then it will kind of form a conduit between the source and drain in terms of charge carriers, in terms of the electron charge carriers. So basically, you set gate to VDD, which is logic 1, and it will electrically connect the source and drain. Now, the thing that's a little nuts about this, though, is that the voltage, now as you guys know, voltage is always, voltage is a potential difference between two things, right? I mentioned that the substrate was grounded. And so if the substrate is grounded, then the gate's voltage is relative to the substrate, right? It makes sense, right? However, once the channel forms, once you get these minority carriers that collect in the channel, that does this thing where it's going to decouple the channel from the substrate. And then your gate voltage potential is no longer relative to the substrate anymore. It's relative to whatever the voltage potential happens to be in the channel, which depends on what's on the source and drain. So it's a little weird to even, like, what is the gate voltage relative to? Well, again, if the transistor is turned off, the gate voltage is relative to the substrate. But if the gate is turned on, if the thing is turned on, then the gate voltage is no longer measured relative to the substrate. It is now measured to whatever the potential is inside the channel, which is affected by what's on the source and drain. So that's why you'll see like voltage of gate relative to drain, voltage of gate relative to source. Now you might say, why the hell would we care about that? Because what happens is that as you turn on the transistor and current flows from source to drain, or drain to source, rather, in the case of an N-type, this thing happens where the relative voltage of the gate starts to drop because the voltage in the channel, and what that does is it pinches off the channel at one point. So in other words, you end up with this thing that happens where if the gate voltage goes beyond a certain level, the amount of current, it caps the amount of current that can flow. And we'll talk more about that in a minute, but just keep that in mind. It has to do with the voltage of the channel relative to either the substrate or the source and drain. Okay, so the pMOS transistor works exactly the opposite way. So in a pMOS transistor, the substrate is an N-type. And the reason why this works, even if you have a P-type overall substrate for the chip, is that you create a well. This is called a well, which is an embedded substrate, N substrate inside the P. And the well, which is the substrate of the pMOS, is actually connected to VDD. So you charge up, this N substrate is at VDD, and that way you get a reverse biasing again, because you can't, if you've got the N charged up to the maximum voltage, you know that you're not going to send any current from N to P. It only goes from P to N. So the pMOS is opposite. You charge the substrate up to VDD, and then the gate, in order to turn the transistor on, you put the gate at ground. So now the gate voltage is, say, 0, and the substrate voltage is VDD, which makes the gate potential look like negative VDD, because it's 0 minus VDD, right? So that gives you a negative voltage. Now you might say, well, how do you do negative? How do you get a negative voltage? Well, remember, it's the voltage of the gate minus the voltage of the substrate. In a pMOS, the substrate's at VDD. So if the gate's at 0, that means that your voltage potential difference between the gate and the substrate is negative VDD. When you charge up the gate charges up majority carrier. When you charge up the gate, so the purpose of charging up the gate is to attract the minority charge carriers in the channel. So the majority charge carriers, they don't really do much. I mean, they're just there. They don't really play any role in the functionality of a CMOS gate, of a MOSFET gate rather. The majority charge carriers don't really do anything. They're just there, and they essentially just implement reverse biasing. But when it comes to turning on a transistor and connecting the source and drain together, that's the job of the minority carriers. So the gate is a capacitor whose purpose is to attract minority charge carriers in the channel. That's the way it works. So like I said, the majority charge carriers really don't do much at all aside from turning off the ability for current to flow, in the diodes that make up the gate. Hopefully that answered your question. So with an N-type, gate is negative charge, negative voltage, and you end up attracting the holes in the channel, which will then connect the source and drain. So it's kind of the opposite. When the gate's 0, it connects. When the gate is 1, it disconnects. That's the pMOS. Okay, so you can think of the N. This is the way that you think of nMOS and pMOS transistors as discrete switches that are either on or off. So this is the symbol. The symbol looks like a transistor. I'm sure you guys have seen that. The gate is the kind of the input, and the source and drain are the two sides of the switch. So if the gate is set to 0, then you turn off the nMOS. But if the gate is 0, you're turning on the pMOS. If the gate is 1, you turn off the nMOS. On the nMOS. And if the gate is 1, you turn off the pMOS. So the nMOS, it's kind of confusing because the nMOS, N stands for negative, but it's not negative logic, it's positive logic, because if the gate is 1, it turns off, and the gate is 0, it turns if the gate is 1, it turns on, and if the gate is 0, it turns off. So the nMOS is the transistor that operates the way you would expect it to. Gate 1 means on, gate 0 means off. That's how you would expect a transistor work. And pMOS is the opposite. And the way you know that it's the opposite is because if you look at the symbol, there's a little bubble on the gate, which looks like the same bubble that you guys are familiar with from 211, which is the logic gate, a little inversion for logic gate. Now, the thing that I always forget is the source and drain. Notice that the drain is on top for nMOS, and it's on the bottom for pMOS. I always forget which way those things go. It doesn't really matter because the source and drain, if you look at the actual way that it's built, there is no difference between the source and drain. It really is more of a question of, they're symmetric. There's no difference in the way that you build the source and drain. It is if you take this design and you split it in half, it's a mirror image. If you split it vertically. But there's a convention for source and drain, and you can see that the idea is that in an nMOS, the current is supposed to flow when the gate is on, it flows from the drain to the source, and in a pMOS, it flows from the source to the drain. But that's not really that important. Okay, so we've talked about diode, we talked about silicon, we've talked about semiconductors, doping. We talked about diodes, reverse and forward bias, and what that means. And then we talked about MOSFET transistors, which are basically just a way to build a capacitor that attracts minority charge carriers and connects two sides, two diffusion areas. So that's really all there is to it. They're not really that complicated. The hard part about these transistors is continuously shrinking them down. That's the hard part, because as you make them smaller, you get all these weird physical effects that start to happen that are difficult to model, and they're difficult to build. Okay, but then how do you take gates and how do you take transistors and build logic gates? You guys are familiar with logic gates from 211. So a logic gate can be built with this style called CMOS, complementary MOS, which is where for every input to your logic gate, you have one pMOS transistor and one nMOS transistor, right? So if you have a 2-input AND gate, for instance, you would have one pMOS and one nMOS for every input to the gate. And the reason for that is because you divide the gate into two networks or two circuits. You have a pull-up network and a pull-down network. The pull-up network is responsible for the cases in which the inputs of the gate would result in an output of 1. That's all. So like if like an AND gate, if there's a 1 and 1 input, if you have two ones on an input of an AND gate, then the corresponding output is 1. And so the pull-up network is the thing that's actually going to be responsible for setting the output to 1 in that case. Likewise, the pull-down network is responsible for any of the input combinations that would give you a 0 output. It would be responsible for that. So what I mean by that is that when I say responsible, what I mean is that if given inputs that result in the logic gate outputting a 1, then the pMOS transistors have to provide a path to VDD. And the nMOS transistors would not provide a path to ground, right? And if you put inputs in that give you an output of 0, then it's the opposite. The pMOSs would basically turn off in a way that would disconnect the output from VDD, and the nMOSs would turn on in a way that connects the output to ground. Now I haven't described yet why we're using pMOSs for pull up and nMOSs for pull down. I'll get to that in a minute, but just keep in mind that you have a pull up network that when you say pull, and I when I was first looking at this, I remember I was confused by the terminology. What's pull up mean? What does pull down mean? Pull up just means that you connect the output to VDD, and pull down means you connect the output to ground. That's all that means. But with a CMOS gate, the idea is that only one of those two networks will be connected to its corresponding side at a time. So when you're pulling up, you're not pulling down, and when you're pulling down, you're not pulling up. They're mutually exclusive. So that way, you only have one of the networks active, not active, but pulling at one time. So that way, if the pull down network is not pulling down, then there should be no path between power and ground, right? There's no way to send current from VDD to ground, because the pull down network blocks you from doing that. And likewise, if you're pulling down, the pull up network is disconnected. So there's no way to there's no connection between the output and VDD, right? So that's the idea, is that you either pull up or you pull down. They're mutually exclusive, and it all depends on the inputs and what input combinations you have on there. Okay, so for example, the simplest gate is an inverter, because an inverter only has one input, and because you have one transistor in the pull up and one transistor in the pull down for every input, then you just have one input. So there's just two transistors. So you always have like you take the number of inputs to the gate and you multiply it by 2, and that's the number of transistors you need in total. But you only need one in of those, one of them is in the pull up and one's in the pull down. So you take an inverter and you have the input, and you have one pMOS in the pull up and one nMOS in the pull down. Now you might be saying, wait a second. How do you differentiate the pull up and the pull down transistors? How do you know what's a pull up and what's a pull down? It depends on the output. So notice the Y is the output, right? The Y is on a node that's connected between these two transistors. And so this electrical node serves as a way to delineate the pull up and the pull down. So basically what you have is a graph that's being bifurcated. You've got an output that separates the two sides, the pull up and the pull down. So the Y, the output, is connected to the middle between the pull up and the pull down. Meanwhile, the input is fanned out to both. So A is connected to both the gate of the in this case the pMOS, which is the only thing in the pull up network, and it's connected to the gate of the nMOS, which is the only thing in the pull down network. And then of course the output's in the middle. So this way, if A is 0, it'll turn on the pMOS, which will turn this transistor on, the top side on, and of course it'll turn the nMOS off, right? So that way you'll be pulling the output up to VDD, because you're simply just saying, it's like throwing a switch, where you throw a switch between Y and VDD. You close the switch between Y and VDD, and you open the switch between Y and ground, right? And on the other hand, if you put a 0, then you close the switch between Y and ground, and you open the switch between Y and VDD. So either you're connecting the output to ground, or you're connecting the output to VDD, depending on the input. And that basically creates the truth table for the inverter. Okay, so now let's return to this idea. Why use pMOSs on the pull up? Why use nMOSs on the pull down? And because this actually creates a problem, actually, because remember that the pMOSs are the counterintuitive gates, the ones that you give a 0 to turn on, right? Well, the problem is that in order to pull the output up to VDD, meaning in order to have any output of 1, right, you have to have at least one of the pMOSs turned on, right? At least one. I mean, I've only showed you one here, right, so far. I mean, obviously you can have more transistors in the pull up and pull down, but let's just consider this case for now. You have to be able to turn on a pMOS or a PFET, you know, a P-type transistor. You have to be able to turn at least one of those guys on to pull the output up, meaning to have a 1 output, which means that in the truth table for the gate, any row of the gate truth table that has a 1 in the output, like we do right here, has to have at least one of the inputs to be 0, because you need that in order to activate the pull-up network. And likewise, every output that has a 0, you need at least one of the inputs to be 1 to turn on one of the nMOSs. And that's based on this restriction that only pMOSs can pull up and only nMOSs can pull down. Now, what's the problem there? Well, the problem is that you can't build an AND gate or an OR gate, because if you look at the truth table for an AND gate, if you want to pull up, you want the output to be 1. In an AND gate, all the inputs are 1, but that won't work, because if you have all the inputs 1, there's no pMOSs will be turned on. So there's no way to pull the output up to 1. Likewise, with an OR gate, if you want to set it to 0, you have to have at least one input to be 1, and that violates what an OR gate is. An OR gate basically says you can't have in an OR gate, the only way to get a 0 is to have no input set to 1. So that's why in CMOS logic, all of the gates are restricted to that rule. Now, so then you may say, okay, well, fine. Why do we have to do it that way? Why do we have to have pMOSs in the pull-up network, right? Why is that? That's because pMOSs are better for connecting to VDD, and nMOSs are better for connecting to ground. And you might say, why is that? Well, remember what I said earlier about the channel. The channel, when you activate one of these transistors, the channel becomes electrically disconnected from the body, from the substrate. And therefore, the reference voltage for the gate becomes relative not to the substrate, but to the channel. The channel is this magical flow of charge carriers channel, right, basically. And that has to do with what's on the source and gate. So in the case of an nMOS transistor, you want the source and drain to be close to ground. Because once you turn on the transistor, the gate voltage is relative to the source and drain, right? And you want the gate to be positive voltage. You want to have positive charge. Well, you're not going to have positive charge if the channel becomes associated with VDD because of the source and drain, right? It's going to be harder. It's going to be harder for the gate voltage to look like a positive voltage, a higher voltage, if you've got that transistor next to the VDD rail. So that's why they say that the pMOS is the pull-up transistor and the nMOS is the pull-down, even though it totally screws over your logic because it makes it so you can't build an AND gate or an OR gate with just in a single gate with a single pull-up and pull-down network. Okay, so that's we'll talk a little bit more about that soon. Okay, so for example, what you end up with is if you have a single CMOS gate, you can do NAND and you can do NOR, but you can't do AND and OR. Remember from 211, an AND is a negative AND gate. So for example, with a NAND gate, the pull-up network are two pMOSs in parallel, and the pull-down network are two nMOSs in series. So if you've got these two guys in parallel, that means if either one of these guys is a 0 input, then you're going to have a 1 output. And in order to pull down, both of the inputs have to be 1. So if both inputs are 1, you connect the pull down through series, two series connected transistors. Both of these nMOSs in the pull down have to be turned on in order to have a 0 output. Likewise, on the pull up network, as long as either one of these two guys are 0, as long as either one of the two inputs are 0, you're going to pull up. So what you end up with is, if you look at the truth table, all the rows, the first 3 rows have a 1 output. As long as you have at least 1 0 on A and B, then you're going to have at least one of those two parallel pMOSs turned on, right? But if both A and B are turned on, or both 1, then both of these two parallel transistors will be off, and both of these serial transistors will be on, and you'll pull down, right? So that's basically what it is that you connect the pull up and the pull down either in series or parallel, depending on how you want the gate to act. And then, of course, the pull down network has to be opposite of whatever the the pull down network has to be opposite of whatever the pull up network is. So if the pull down network is in series, the pull up network is in parallel, and vice versa. So in an AND gate, the pull down network is in series, and in a NOR gate, the pull down network is in parallel, right? So, and then of course the pull up network is the opposite. So that's how you build these logic gates out of these MOSFET transistors. And this is what CMOS logic is all about. The reason why it's called CMOS is that the pull up and the pull down networks are complementary, meaning they're complementary not only in terms of serial and parallel, but they're complementary in terms of, the logic as well. You can only have one on at a time. You're either pulling down or you're pulling up, not both. And that's the reason why the chips semiconductor technology has progressed as it has, because only one of these is on at a time. You don't have any static current leakage from VDD to ground, because you're not going to have the pull up and pull down network on at the same time. And because you have no static leakage, these are very power efficient. They're very energy efficient devices, which is why you can put billions of them on a chip. And it uses relatively small amount of power as compared to using like a pull-up resistor, as we did with I²C. Okay, so anyway, I'm out of time. That's it. Any questions? Okay, great. So next time we'll continue with this. Hopefully I should have a quiz ready for you on Monday on this stuff that you'll have a week to take. Okay, thank you all. Have a good weekend.